Welcome to Math Throughout the Ages, where we'll still be talking about the history section of math. And in today's lesson, we'll be talking about medieval Europe, and hopefully the plan is to finish all the way to mathematics today, but I'm not sure if I can get through all this stuff, because I myself don't really understand calculus that much. Let's get this started with. Alright, it's medieval Europe, it's around 9th century, and the political and social life in Western Europe has become, well, at least stable enough so that people in Western Europe could now pay attention towards education. You know, the good stuff. And many schools, cathedral schools, popped up. Technically schools that were by the churches. And they learned grammar, logic, math, and arithmetic, geometry, music, and astronomy. And it was very likely that few students actually studied the mathematical topics in like quadrivium, but their presence in that curriculum that they offered in mathematics helped stimulate interest in the mathematics anyway. Now, once you learned all the math that these cathedral schools could teach you, where was the best place that you could learn more math? The best place at the time was in the Islamic places, and the best option to go and access these places were in Spain, because, well, Spain was right next to one. And as soon as those Westerners went ahead and went back to the Islamic Empire and saw all those mathematical texts that none of the Islamic people seemed to really care about, they seemed to more care about the alchemists, the scientists, and those kind of stuff, and they found out about this guy named Al-Khwarizmi who created this thing called algebra. Well, they went ahead, hooked into it, took these texts back home, and worked on them lots and lots and more. They went ahead and created books of squares. They created quadratic equation, but I'm getting a little too ahead of myself. They essentially created this field of mathematics known as practical geometry. This is where my knowledge starts getting fuzzy because I haven't even started high school yet, and I'm trying to explain high school math without even learning high school math. Wish me luck. Anyways, practical geometry itself came in, and they went ahead and created, well, they revealed and created themselves their own creative and talented mathematicians. Like, they created quadratic equations. One of the most easy ones is this: x plus 1 squared, and then the answer will be -1, but you can't exactly just get like a negative area. Fortunately, -1 times -1 is 1. But what about this? We'll talk about that problem later. The 15th, 16th, actually the 14th, 15th, and 16th centuries themselves have went ahead and created several beings and several nuts of mathematics. Jesuit schools were one of the most prominent places where you could go ahead and learn all this mathematics. And then universities started offering these courses because people started learning about these stuff. And during Europe, well, there was this interesting thing about mathematics. But we're still stuck in algebra, so I can't really talk to you about quadratics yet. And one of the few things that really happened was the relationship between algebra and trigonometry. People finally realized that algebra and trigonometry are one way or another linked. You can't just separate these two and be like, algebra, no, I want to be an algebraician, and I want to be a trigonometrician. You can only be a mathematician. You can only learn algebra. You can only learn trigonometry after you learn algebra. Also, you don't need to learn trigonometry to learn some algebra. And they went ahead and learned all about these literal trigonometric functions. Some of the ones being sine, for some reason they spell it S-I-N-E, cosine, tangent, cotangent, and the secant and the cosecant, which all became pretty much standardized, but all you need to know right now is the sine, cosine, and tangent. One of my favorite methods to go ahead and remember the sine, cosine, and tangent is this. Let's say I want to find the sine of theta. Well, then you can just use this. If you want to find the cosine of theta, here you go. And you want to find the tangent of theta, here you go. And this only works for right angles, unfortunately. Or you could just try a different popular method. It's called SOHCAHTOA. Sine opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse. And tangent is opposite divided by adjacent. And yeah. And as soon as you change theta, everything gets wonkers. And if you try to find the theta, like the sine of 90, well, good luck finding the opposite of it divided by the hypotenuse of it, because it's the hypotenuse divided by the hypotenuse, which is equal to 1. And it has 2 adjacent sides, so good luck even finding the cosine of it. But seriously though, that's all you need to know about trigonometry: sine, cosine, tangent, and I just explained to you some math again and no history. They themselves, let's go back to the geometry in the 14th, 15th, and 16th centuries. They themselves started need to create some rules on how to draw 3D shapes. Like nowadays, we know that we needed to go ahead and draw 3D shapes like this. It's like a little convention that we made ourselves. But back then, they had no idea what it should even look like. So they wanted to study these objects, and try to draw them as a 2D representational object because, well, you can only draw on a 2D shape. You can only draw on a paper, which is 2D. And they learned about depth, they learned about like height, width, length, and kind of stuff, and they taught themselves how to draw like several things like spheres and pyramids and how to make it see-through. This would not only help mathematicians, but also painters like Leonardo da Vinci, who would go ahead and improve on these methods to make them look a little more, let's say, more 3D and realistic. And some people, like the famous Albrecht Dürer, were quite sophisticated in their understanding of all the geometry involved. In fact, Dürer himself wrote the first printed work dealing with the plane curves that went beyond both in his paintings and his artistic works of his contemporaries. He wasn't just an artist, he was also a mathematician. And then algebra comes to age. As we reach early modern times, mathematicians began to get broader and more diverse, and then algebra eventually just kind of stopped. There was a limit to algebra, obviously, and then quadratic equations happened, and then we finally needed to go ahead and start working on trigonometry and calculus. Except calculus hasn't reached yet. No one has figured out calculus yet. It isn't Newton's time yet, so yeah, we're stuck here. Oh, and this is where the juicy part comes in. You know that, like back then, instead of mathematicians working together, like how Asians or Islamic people do it, the Europeans mathematicians had to go ahead and get their reputation by doing these, how should I describe it? These so-called math duels. And within these math duels, they would go ahead and challenge other mathematicians in, dueling about math, especially quadratic equations, where people, mathematicians specifically, figured out solutions to some equation, let's say x4 plus x cubed plus 5x squared plus x plus 4. And then after finding out how to solve these equations, they would invite other mathematicians towards it, hey, come here, let's do some math together. Whoever wins is the best man ever. And they would never reveal their solutions, which is unfortunately why there was not so much literature about the solutions towards all this nowadays, or at least back then. One of the most famous ones being this guy named Tartaglia and Cardano. How this work was, well, yeah. In the case of a cubic, let's talk about the cubic solutions. In the case of the cubic, there's this guy named Cardano. Cardano promised, he went ahead and asked Tartaglia, who was shown to really know how to solve the cubic, merely because his mentor died and shared the secret with him. He never told them how he made the solution for the cubic, so that he was stuck on how to find the solutions of other polynomials. Tartaglia was the only one known to know how to solve cubics, and Cardano went ahead and asked him for the secret. He was "Senpai, teach me how to get me this ultimate power," and he got the ultimate power, and then realized that he figured that out himself already, and there was already how he could do it, and he figured out how to solve other polynomials. He challenged Tartaglia to solve other polynomials higher than the cubic, and Tartaglia was like, dang, this guy's okay, I'm stuck. And then Cardano was like, hey, I did it. And it worked out pretty fine. And then Cardano was like, I'm going to publish a book. But he remembered he swore to secrecy about Tartaglia's secret. It was like, but hey, I made this up. I already found this myself. I'm not allowed to share this part. I'm going to acknowledge this part. But I can share this with the community. Of course, Tartaglia was extremely furious. But there's nothing he could do about it. Because by the time he found it, thousands of copies were already sold. And to this day, that formula is known as Cardona's formula. It was pretty fun, those math duels. People would duel each other in math until they realized that it was probably better to just come together, work together, and do stuff together. And now we arrive to the part I dread most. Calculus! Calculus! This is when Newton came in. Also, it's arguable that other people invented calculus before Newton did. I'm just gonna credit Newton because he's the only name I can think of. Of course, in the late 16th and early 17th centuries, while they were still developing algebra, another group of people were beginning to use mathematics and try to understand the universe. At this time, they were called natural philosophers, one of the most prominent ones being Galileo Galilei. Galileo. And he himself insisted, including astronomy and physics of both all those moving bodies. He himself blended observation and experimentation with all the mathematics. In fact, he himself insisted that mathematics was the only way he could understand the world in its purest form. And he wasn't alone, and he wasn't wrong either. There was this other famous dude named Johannes Kepler, who also understood the entirety of scene. Kepler himself discovered that planets moved around the sun in elliptical orbits and formulated mathematical equations to just describe these orbits. He even created a thing called mathematical laws to go ahead and describe how each of these orbits reacted and moved and how they acted. Like how they acted and reacted. Get it? Okay, that's a very bad pun. And this went ahead and taught us about things like volume and stuff. And we started imagining things a little differently. This is when we started developing theorems for volumes. Like you could go ahead and you cut a cylinder into several circles. You cut it into several circles, and then you just combine the area of all the circles together, and boom, you just got yourself a little nice sweet cylinder. At least you know the volume of a cylinder now. You know how much stuff you can put on the cylinder now. You could even go ahead and split a sphere into all these different little sections, and then you just combine them together, and well, boom, you just created yourself a nice little volume of a sphere. Like, just add all these together, and boom, you're just done. But then they created all those mathematical formulas to go ahead and describe it, like pi r squared h for cylinders, a third of that for cones, 4/3 of pi r cubed for the volume of a sphere, and etc. Phi itself is a really interesting phenomenon. And out of all the many things that went ahead and, explained all this math stuff, eventually we had one of the most important of them. One of the most mathematically important texts of all time, we had the Principia, which is written by none other than our own Sir Isaac Newton. You know, the guy who was known mostly for, discovering that gravity existed by having an apple literally fall onto him. Yeah, it's this guy. In the book itself, he went ahead and described calculus, which, as far as my knowledge goes, is finding something like the area of curves by going ahead, splitting the area of curves into rectangles, and then making infinite numbers of those rectangles so that eventually you just get the curve. And essentially that would be the entirety of calculus. I have no idea how calculus exactly works. I have yet to study calculus myself. But essentially, this is how calculus works, apparently. You go ahead, you learn about all this, and then this went ahead and taught us several things about mathematics, and this is usually the highest this is usually the highest point of mathematics taught in the high schools. Usually that's about it, but I heard of some high school students learning higher and much more beyond stuff. And then in the 19th century, we saw a huge explosion in mathematical activity and significant changes in how mathematicians did their work, especially in science and commerce. This is still the 18th century, and the computer still didn't exist yet. But then we finally go ahead and find out about all these different shortcuts. Now that we knew, most of math, at least most of the math that we know nowadays in modern times, we could go ahead and start finding ways to make doing that faster. I don't think you divide this by 500s, this by hand. I don't think you'd want to do that. But we started finding shorthands of all these mathematical expressions, and we went ahead and found all those general formulas and everything as well too. There was everything. We found permutations, formulas, and more math duels. Unfortunately, math duels died out, and we started using mathematics to help create stuff, like, for example, the Eiffel Tower. Yippee-ki-yay, I myself went to the Eiffel Tower. Never went up the Eiffel Tower though, unfortunately. And this trend toward mathematics started becoming one of the most important things ever. Mathematics started becoming a degree. We started becoming more abstract in mathematics because we found that practical mathematics had a limit in our modern day world. But we wanted to find out more about mathematics. So we went ahead and learned more about mathematics. And eventually we asked ourselves, what is the square root of -1? Because unfortunately there is no such thing as a negative square, because the definition of square is a number times that same number, except 1 and -1 might be the same absolute value, but it is obviously not the same number. So this cannot exactly be a square, but on a coordinate plane it has the same side length, so technically it is a square, right? I mean, how can the square have -1 area? Now, what's the square root of -1? Obviously, this question remained unanswered for a while. But instead, we just started using this for our own advantage. We just replaced that with I. I think imaginary itself isn't one of the best numbers ever. One of the best names ever, because I is definitely not imaginary. But because everyone else is calling it imaginary, I'm just going to call it imaginary. We go ahead and use this as a property as well too. And this helped us solve several several solutions. Like we've been able to at least solve mathematical equations ourselves now. And then we have -1 here, and we have -I here, and it always comes back. Like, one of the special properties of I is that it always comes back how much power you come back. Like, if you multiply I by itself by 4, you're like 1, 2, 3, 4. You always go back to I. Like, I squared is -1. And -1 times -1 is apparently 1. And then we started finding things where we found that it was impossible to prove, and so we had to prove that it was impossible to prove. We never imagined that would happen. And then computers started existing. Alan Turing started making these computers. And then we started finding out calculators were a great handy-full device. And we started making all those calculations way easier. And these computers themselves have made our lives way easier and has made our day. Like, without Desmos, I could probably never find the solutions to this. Like, without computers, I definitely cannot graph this within a few seconds. If you're human, then you wouldn't be able to. And this is why computers came in so handy. Computers themselves have helped us go ahead and be able to compute things too. We were able to finally compute to pi to the... Like, we were able to calculate pi to this 300 trillionth digit, which is about 299.999999999 trillion decimal places. Pretty amazing if you ask me. And then, this is where we are today. The world of Desmos, the world of AI, now doing your math for you. AI is pretty inaccurate about math in the olden days, but now it's pretty accurate. So, here we are. We finally finished mathematics. Mathematics today isn't just like, oh, I created a new number. Oh, I created this. No, it's not that anymore. It's just creating a new way that we can use math. We go into a realm we haven't known, we haven't explored, and then finally, we make up something new in the world of mathematics. Probability theory, statistics, or maybe something in algebra. Highly doubt it will be in algebra though. We are still able to create mathematics. They're probably going to need to make a new edition soon. And I really hope you guys enjoyed this episode. I finally finished the history part of this, and then I'll talk about the math part next time. I hope you guys enjoyed this episode, and until next time, Shihon out, peace. Bye bye.